Neutron stars are among the most extreme and violent objects in the universe, tiny, ultra-dense remnants of massive stars that have collapsed under their own gravity. They are essentially giant atomic nuclei, only a few kilometers in diameter but containing more mass than an entire star. Their existence is a direct consequence of the death of something majestic. The life and death of stars. Stars exist in a delicate balance. Their immense mass, millions of billions of trillions of tons of hot plasma, is constantly being pulled inward by gravity. This compression generates the extreme temperatures and pressures necessary for nuclear fusion, where hydrogen fuses into helium, releasing energy that pushes outward and counteracts gravity. As long as this balance holds, stars remain stable. But eventually, their hydrogen fuel runs out. Smaller stars, like our Sun, go through a phase where they burn helium into carbon and oxygen before eventually fading into white dwarfs. However, in stars many times the mass of the Sun, things take a far more dramatic turn. When helium is exhausted, the balance shifts momentarily in favor of gravity, causing the core to shrink and heat up. This triggers the fusion of heavier elements. Carbon burns to neon over centuries. Neon fuses into oxygen in a year. Oxygen turns into silicon in mere months. Finally, silicon fuses into iron within a single day. Then, everything stops. The birth of a neutron star. Iron is the end of the road for fusion. It cannot release energy. With no outward pressure to counteract gravity, the core collapses in an instant. At this point, something incredible happens. Gravity squeezes electrons and protons together, forcing them to merge into neutrons. The core, once the size of Earth, shrinks to just 25 kilometers across, forming a neutron star. The entire star collapses inward at nearly 25% the speed of light before violently rebounding in a titanic supernova explosion, outshining entire galaxies. What remains is a neutron star, an object so dense that a single cubic centimeter of its material would weigh 1 billion tons. That's like squeezing Mount Everest into a coffee cup. The extreme world of neutron stars. Neutron stars push the limits of physics in ways we can barely comprehend. Gravity, their gravity is second only to black holes. Light bends around them, allowing us to see parts of both the front and back simultaneously. Heat, their surface temperatures soar to 1,000,000 degrees Celsius, compared to the Sun's mere 6,000 degrees. Magnetic fields, they possess the strongest magnetic fields in the universe, up to 1 quadrillion times stronger than Earth's. Inside, neutron stars resemble both stars and planets. They have a solid crust over a superfluid core. The outermost layers consist of iron in a crystal lattice, with a sea of electrons flowing through. Deeper down, nuclei are packed so tightly that they merge into bizarre structures called nuclear pasta, the strongest known material in the universe. Beneath this, the core may hold an exotic soup of quarks, though its true nature remains a mystery. Pulsars, magnetars, and cosmic collisions. Newly formed neutron stars spin incredibly fast, like a figure skater pulling in their arms, sometimes rotating hundreds of times per second. This rapid rotation, combined with their intense magnetic fields, produces beams of radio waves that sweep across space. These pulsars are some of the best-known neutron stars, with around 2,000 identified in the Milky Way alone. Even more extreme are magnetars, neutron stars with magnetic fields so powerful they can disrupt electronics from thousands of kilometers away. But the most spectacular events occur when neutron stars exist in pairs. Over time, they spiral inward, losing energy through gravitational waves. When they finally collide, they unleash a kilonova explosion, scattering neutron-rich matter into space. Amazingly, this is how many of the universe's heavy elements, gold, platinum, uranium are created. Neutron stars don't just die once, they die twice, leaving behind the building blocks of future worlds. The legacy of neutron stars. Over millions of years, the elements forged in these cosmic furnaces mix into new clouds of gas and dust. Eventually, gravity pulls them together again, forming new stars, planets, and even life. Our own solar system is a product of this cycle. The atoms that make up our bodies, our planet, and our technology were once part of ancient neutron stars that lived and died billions of years ago. And that's pretty amazing. Key characteristics. Density. Neutron stars are the densest objects in the universe, after black holes, with a density comparable to that of an atomic nucleus. Size. They are remarkably small, with a diameter of about 12 miles 20 kilometers. Magnetic fields. Neutron stars possess extremely strong magnetic fields, which can be millions of times stronger than Earth's. Rotation. They rotate rapidly, sometimes hundreds of times per second, due to the conservation of angular momentum during the collapse. Pulsars. Some neutron stars, called pulsars, emit beams of radiation, radio waves, X-rays, and gamma rays from their magnetic poles, creating the effect of a lighthouse beam as they rotate. Temperature. Neutron stars are extremely hot when they form and cool slowly over time. Composition. They are thought to be composed primarily of neutrons, with a solid crust of dense iron. Observational evidence. Neutron stars are observable due to their strong magnetism, rapid rotation, and emission of radio radiation in a narrow cone.